The LM4F 120 H5QR is equipped with a 12 megabit per second USB 2.0 compliant USB device port. USB ports on other Stellaris devices have on-the-go and host modes as well as device, but this LM4F part is cost reduced to have just the device port. In Chapter 6, you'll look at the basics of USB and how the USB port is implemented on our device. Reviewing some USB basics, obviously USB connectors come in multiple sizes, as you can see on the top right there. Most of them have 4 pins, power, ground, and 2 data lines called D plus and D minus. Some of the connectors have a 5th pin ID for USB 2.0 connectors. If you take a look down at the diagram on the bottom right, it'll show you that the pins for the power are slightly longer. That way the power will be connected first and then the data. The different standards that are out there, USB 1.1 defines the host as the master and the device as the slave. Speeds to 12 megabits a second, and that devices can consume 500 milliamps once they're enumerated, 100 milliamps for startup. USB 2.0, that's where our USB ports are compliant. The speeds are as high as 480 megabits a second, but you can be at full speed, which is 12 megabits a second, and still be compliant. USB 2.0 also includes the on-the-go addendum, where devices can be host, device, or they can decide which they're going to be during enumeration. New out there is USB 3.0 with speeds to 4.8 gigabits a second. Of course, they're going to have new connectors to support that with split up data, transmit and receive data lines. Most USB products that are sold are slaves. For instance, a USB flash drive. A USB host, normally that's some kind of a PC or computing device, but it can be embedded. USB on the go, that's dynamic switching between the host and device roles. You can connect 2 on-the-go ports together and they'll undergo a host negotiation to figure out who's going to be in control. For instance, if you cooked your computer to your digital camera, you'd certainly want your digital camera to be a slave to your PC's host. But if you take the digital camera and connect it to a printer, you would want the camera to be a host to the printer's slave so that you could print to it. The host polls each device at power up, and information from the device is going to include the device descriptor. That's the manufacturer and product ID so that the host can find the driver if it needs one. A configuration descriptor that includes the power consumption and any interface descriptors that are required. The endpoint descriptors, that's the transfer types, whether it's bulk, isochronous, the rest of those, the speed, and so on. The process of the host querying the device for all of these structures and then configuring itself is called enumeration, and that's what allows plug and play to operate. The USB port on the LM4F 120 H5QR is a USB 2.0 device that offers full speed, that's 12 megabits a second, and it goes down to low speed, which is 1.5 megabit per second operation. The device has an integrated PHY on it, so the hardware connection to the USB port is very simple. We offer transfer types, all the major ones: control, interrupt, bulk, and isochronous. We also offer device firmware update in ROM, so you can plug this LM4F 120 H5QR, you can plug it into a host and do device firmware update across to it. On other Stellaris devices that have host mode, they can also offer that you can plug in, say, a flash drive with the correctly formatted files on it, and it will do a device firmware update from a device as a host, and all you have to do, like I said, is have the correct files in it. Stellaris Collaterals. TI is a member of the USB Implementers Forum, and Stellaris is approved to use the USB logo. The stacks, the hardware, and so on are certified USB compliant. We also offer vendor and product ID sharing. We have that's also called VID and PID. It costs a certain amount to go to the USB organization and buy the vendor ID and product IDs. We can have you If you fill out a sharing agreement, you can utilize product IDs underneath our vendor. This is perfectly legal. The block diagram for the USB peripheral is shown at the top of this slide. This is an integrated USB controller and the PHY, the physical connection that offers up to 16 endpoints. Now, anytime you connect a USB device to a host, there is one dedicated control in and one dedicated control out so that you can do the enumeration across there. And then there are up to 7 configurable input endpoints and 7 configurable output endpoints. As a part of the controller, there's a 4K dedicated endpoint memory. That's a single 4K, not per endpoint, and that's not part of the device SRAM. That's inside this peripheral. There are separate DMA channels, up to 3 in endpoints and 3 out endpoints that you can use from the peripheral to transfer directly to memory. One of the endpoints can be defined for double buffered 1 KB isochronous packet size to facilitate moving large groups of data across this port. TI's StellarisWare USB library is a license-free and royalty-free set of drivers, stack, and example applications for Stellaris microcontrollers. Now, like a Ethernet port, like a CAN port, there is a stack that that you interact with to send information back and forth across the USB port. Of course, you can do it yourself. You can write your own peripheral driver code and write through the ports using just the peripheral driver library, but it's a lot easier just to talk to the stack, and we have a stack as part of StellarisWare. Now that stack supports host, device, and on the go, but of course the LM4F120H5QR, that USB port is device only. The stack software and everything, it builds on top of the DriverLib API. It adds a framework for a generic host and generic device functionality, and it includes implementations of the common USB classes that we talked about earlier. It has a layered structure, so you can go in and dial in the amount of control that you want to have over the software. I'll show that on the next page. The drivers and the INF files are included where that's appropriate so that you can communicate back to Windows with them. I mentioned before, the Stellaris microcontrollers, the hardware and the software have passed USB device and embedded host compliance testing. So if you want to go off and get the certified USB certification from the USB organization, you can go do that and stamp your product with the certified USB decal. Some of the device examples that are available are the human interface device for the keyboard. This is where this device, say the device itself will act as a keyboard, the device itself will act as a mouse. We could do mass storage to the device, audio, device firmware upgrade, the LM3S 3748 and act as an oscilloscope. We have implementations for serial and for bulk to store, and that's one of the things that we're going to be doing is the bulk example. We have Windows INF files for supported devices to point to the base Windows drivers. Some of these applications have drivers in Windows. You don't need to do anything. Those will also help you set the config string, set the PID and VID, and there's a precompiled DLL that's going to save you development time. And all that device framework is integrated into the USBLib and the stack. You can decide on what level of customization that you want to deal with when you're working with the USB APIs. If you take a look at the far left, application 1, you just want to pass simple data to a higher level API. For instance, the you want to customize the mouse human interface device. So you're going to build on top of the host and device class APIs, the class driver, device class driver APIs, the host controller device, and the DriverLib API. This is what's going to implement the entire stack for you. You can increase your level of customization as you move all the way over to the right, where, for example, you would implement your own USB protocol using DriverLib. This would be where you'd go off and For instance, you might purchase a third-party USB stack, or you might go off and write your own. Obviously, to the far left is less time spent developing your USB software, and the far right can be a lot if you're going to write it yourself, or if you're going to purchase a third-party USB stack because it has some capability that you require. In Lab 7, you'll use a StellarisWare code example to implement bulk transfers of data from your laptop host to and from the USB port on the Launchpad. You'll use a small Windows side application to send and view data while also watching messages on the terminal display. You'll also use the emulator to view transferred data in the LM4F 120H5QR memory. There are 4 types of transfer endpoint types in the USB specification. Control transfers for command and status operations, interrupt transfers to quickly get the attention of the host, isochronous transfers, which are continuous and periodic transfers of data, and bulk transfers to transfer large, bursty data. Before we start poking around in the code, let's take the StellarisWare example called USB under bulk under example for a test drive. We'll be using a Windows host side command line application to transfer strings over the USB connection to the Launchpad board. The program there will change uppercase to lowercase and vice versa. Then transfer the data back to the host. In Lab 7, Step 2, the USB bulk example project is one of the StellarisWare examples. When you import the project, note that it will automatically be copied into your workspace, preserving the original files. If you want to access your project files through Windows Explorers, the files you are working on are in your workspace, not StellarisWare. If you delete the project in Code Composer Studio, the imported project will still be in your workspace unless you tell the dialog to delete the files from the disk. Click Project, Import Existing CCS Eclipse Project. Make the settings shown below. That's from StellarisWare, Boards, the EK LM4F 120XL, USB Dev Bulk. Notice that the copy projects into workspace will be automatically selected. And click Finish. In Step 3, make sure your evaluation board's USB debug port, as shown, is connected to your PC. Build and download your application by clicking the Debug button on the menu bar. Remember, if you left your device with Hibernate code programmed in the flash, you need to make sure you wake your device up by pressing and holding SW2. In Step 4, click the Terminate button, and when Code Composer returns to the Edit perspective, unplug the USB cable from the Launchpad's debug port. Here. Move the Power Select switch to the device position, that's nearest the outside of the board, and plug the USB cable into the USB device connector on the side of the Launchpad board. The green LED in the emulator section of the Launchpad here should be lit, verifying that the board is powered. In a few moments, your computer will detect that a generic bulk device has been plugged into the USB port. Now, the one that we're recording here may not, since we've already done this a few times. Similar to the device installation in Module 1, install the driver for this device from c:/StellarisWare/Windows drivers. In your Windows Device Manager, you should verify that the Stellaris, why don't we do that? We'll bring up the Device Manager. We'll verify that the Stellaris bulk device is correctly installed, and that should be down near the bottom. There we go, Stellaris bulk device. Okay, we can close the Device Manager. The Step 6, make sure that you installed the StellarisWare Windows side USB examples from www.ti.com/StellarisWare /sw-usb-win as shown in Module 1. In Windows, click Start, All Programs, Texas Instruments, Stellaris, USB Examples, USB Bulk Example. The window below should appear. In Step 7, type something in the window and press Enter. For instance, all caps TI, as we show here. You can see we have wrote 2 bytes to the device, expected 2, read 2 bytes from the device, expected 2, and the return string from the device is lowercase ti. The host application over on the PC sends 2 bytes representing TI, capital TI, over the USB port to the Launchpad board. And the reason that we've done this here is to show you that there's only one way that we can be communicating with the board, and that's through the device port, not through the emulator port. The code running on the LM4F device will change the uppercase to lowercase and echo the transmission back up through the USB port. Then the host application will display the return string. Feel free to experiment. Now that we're assured, if you want to type something else like, you do it, there you go, great. Excellent. You can see it's changing uppercase to lowercase and vice versa. So now that we're assured that our data is traveling across the device USB port, we can look into the code a little bit more. Type all caps exit to terminate the USB bulk example program on your laptop. Now, I'm going to connect the other USB cable from the PC to the debug port on the Launchpad. And I'm going to switch the power select switch back to the debug position. The green LED in the emulator section should be lit, telling us that the device is powered. So now we have both ports connected to your PC. This is going to mean that we can transfer data back and forth through the USB device port, as well as perform emulation and do some other viewing of the memory through this port right here. In Step 9, in Code Composer Studio, if USB underdev underbulk.c isn't already open, expand the Project and Project Explorer pane and double-click on the USB dev bulk.c program. The program's made up of 5 sections, and we want to go ahead and take a little look here through it. The systick int handler, that's an ISR that handles interrupts from the systick timer to keep track of time. The echo new data to host, that's a routine that takes the received data from a buffer, flips the case, and sends it back to the USB port for transmission. The TX handler, that's an ISR that will report when the USB transmit process is complete. An RX handler, which is an ISR that handles the interaction with the incoming data, and then it calls the echo new data host routine. And then finally, the main routine, which is primarily initialization, but there's a while loop there that keeps an eye on the number of bytes that have been transferred. If you're looking through the code, look at the UART printfs. Those APIs are sprinkled throughout the code. This technique is known as instrumentation. We instrument the code, allowing us to monitor its status through the UART port. UART transfers will be done through the emulation port. So in Step 12, we're going to want to take a look at the instrumentation. So as shown earlier in Module 1, start your terminal program and connect it to the Stellaris virtual serial port. Ours was COM34, yours is probably different. The speed is 115/200. We may need to press Enter. Okay. So arrange the terminal window so it takes no more than 1/4 of your screen and position it in the upper left-hand corner of your screen. In step 13, resize Code Composer so it takes up the lower half of your screen. Click the Debug button to build and download the code and reconnect to your Launchpad. When the process is complete, run the code by clicking the Resume button. So you can see we started the example. You can see that it reported its status back up through the instrumentation. So now let's go ahead and start the USB bulk example Windows application as shown in step 6. Place the window in the upper right corner of your screen. Okay, why did I do it this way? What I did was I set up the terminal program in the upper left so that when the program that we were controlling from Code Composer Studio, when we turned that on and ran it, it would report its current status to the terminal window. Now, the USB bulk example has to connect to the USB port. That USB port isn't there and isn't running until the code is running in Code Composer Studio. So that's why I did it in that sequence. I put the terminal up there, I started the program, and then we put the USB bulk example so it could talk to the USB port. So while this is nice on a single screen, it sure would be a lot easier if we had multiple screens. In step 15, note the status on your terminal display. Your terminal has basically, it just says host connected right here. Let's type something like all caps Texas Instruments into the USB bulk example Windows application and press enter. So what we should see, the return string is lowercase Texas Instruments. The number of bytes was 17. And if we take a look at our instrumentation in the terminal window, you see it's transmitted 17 and received 17. Okay, in step 16, click the suspend button in Code Composer Studio to halt the program. So remember, as a summary, we're sending bulk data across the device USB connection. At the same time, we're performing emulation control and sending UART serial data across the debug USB connection. Not bad for $4.99. If you get things out of sync here and find that the USB bulk example won't run, remember that it has to be started after the code on the Launchpad is running. So now we want to take a look at the buffers that are going on down on the LM4F device. In step 17, remove all existing expressions, if you have any, from the expressions pane by right-clicking inside the pane and selecting Remove All. We don't have any. Down around lines 503 and 504 in the code, you'll find the USB buffer inits for the transmit and receive buffers. One at a time, highlight the G_STX buffer and G_STX buffer and add them as watch expressions. Now, by the way, we could have watched the buffers in the memory browser, but this method is a little easier to see and quite a bit more elegant. So now we don't need to see the code. Expand your buffers in the expressions window so we can see everything as much as possible. I think we didn't have the entire. I think we grabbed the close brace right here. Yes. 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 So we can get rid of that first one. We had the closing paren there, and it didn't like that. Very nice. View the expressions. Very nice. Drag the code window down. We don't need to see that. Very nice. Very good. The main thing we're going to, we may need to move this up and down a little bit because our screen is fairly small. So if you take a look at the two different pieces here, you can see in the transmit buffer, you can see lowercase Texas inst right there. In the receive buffer, you'll see uppercase Texas inst. So the arrows, those will also point out, if you want to take a look at these in your memory browser, you can see those are the addresses at 20,400,000 and 20,500,000. Those are the addresses of the values. Unfortunately, the expression window only shows us the first 10 bytes in the buffer, so anything after that isn't going to show. This code that's running on our device uses both buffers as circular buffers. Rather than clearing out the buffer each time data is received, the code appends the new data right after the previous data in the buffer. When the end of the buffer is reached, the code starts again from the beginning. You can use the memory browser to view the rest of the buffers if you want to, if you don't believe it says instruments in there. In step 20, resize the code window in the debug perspective so you can see a few lines of code. Around line 331 in the C file, find a line of code containing the if under UL event. This is the first line in the TX handler ISR. At this point, the buffers hold the last received and transmitted values. Double-click in the gray area to the left of the line number to set a breakpoint. Resize the windows again so you can see the entire expressions pane. Save a little space down there so we can change the, we'll have to, that's good right there. Move down so that you can see the breakpoint in the window. It's not too far down there, it's just a little ways. There you go. Double click, right click, excuse me, on the breakpoint and select breakpoint properties. Change the remain halted action to update view and click OK. In step 21, click the core reset button. We don't have our debug window open, so we can do a view debug. There we go. We can hit the core reset button, that one. Very good. That will reset the device. Make sure, we also need to make sure our view is expanded in the expressions pane, and then we're going to click the resume button to run the code. You need to go back to view the debug window, click the resume button, then we can review the expressions window. We're a little restricted on space right here. Very nice. Now expand the buffers. I guess we have them in there multiple times. That top one's, we can just kill that top one. Okay, at this point, remember that the USB bulk example has no doubt lost link with the board, so close the USB bulk example by hitting the X, restart it. So now it's reconnected with the board. In step 23, since the expressions view will only display 10 characters, we want to try something short like TI. So all caps TI. So now you can see that the received buffer says TI. If we drag the code window down, there we go. Now we can see that both of them are in there. When the code reaches the breakpoint, the expressions pane will update with the contents of the buffer. Try typing uppercase is. Now after a moment you'll see TI is appear in both windows. After the breakpoint it updates with the contents. Now type something like awesome. Excellent. Notice The E was the 11th character, and it's not displayed in the expressions pane. In step 25, when you're done, close the USB bulk example and terminal program windows. Click the Terminate button in CodeComposer Studio in case you have to bring up the windows as it was before. You can always click Windows Reset Perspective if you've moved things around. Excellent. Close the USB Dev Bulk project in the Project Explorer pane and minimize CodeComposer Studio. We will also disconnect and store the USB cable that's connected to the device USB port.